Okay, so now what we're going to do, we've introduced some of the basics for circuits, the things that we're going to be talking about. Potential difference, aka voltage, current, and resistance. Now we're going to see if we can piece together a relationship between them. To start off, let me explain what I've got. I've set up a series of circuits for us to explore. I'm going to take a look at A, which is a light bulb, one of the light bulbs from our circuit kits, and then B through F, B, C, D, E, F, are all resistors, actual resistors, the kind that you would find in different pieces of equipment. So they have actual resistances that we're actually going to, we'll take a look at. So we've got, this one is marked R7, R1, R2, R3, R4. Those are the notations that they have in our circuit kits. But each of them is a different resistor. Now, we've got our resistors, and we're going to see if we can explore a bit about them. However, we're also going to need things that get us information. If we want to find out about the resistance, we want to find out its relationship with the potential difference, the voltage, and the current, measured in amps. So, first and foremost, I've got this. This is a regulated DC power supply. Now, this one's nice because it's limited to 2 amps. It won't let us draw too much current that might be problematic. That being said, it's not something that you want to just leave on lying around. Pay very careful attention when we're using these in class. They can be dangerous like any other electrical equipment. 2 amps is a large amount of current. Now, the nice thing about it is it's got an on-off switch and a light that comes on, red light right here, when it's on, so you can tell easily when it's on or off. There's also a dial. We go from 3 volts to 4.5 volts to 6 volts, 7.5 volts, 9 volts, and 12 volts. And you've got a little slider that you can move it to each of those. We're going to be doing that throughout this lab that we're going to take a look at. Now, I've got a couple different options on this. Right now, I'm going to start off with this happy little character, which is called an ammeter. It's a galvanometer. And what it's going to do is I'm going to adjust the electric potential difference, and I'm going to see what happens to the current. This happy little character will measure some current, so I'll point it towards you. Let's get it put into an appropriate spot. I've got to wire this up properly so that my circuit will actually work. But I've got that set up and an easy way for us to adjust this as we go through. So here we go. I'm going to turn this on. Watch the needle. We can see that the needle goes up and our light bulb comes on. In fact, this is one of our first data points that we're actually going to collect, but I'll get back to that in just a moment. So I'm going to point this back at me so I can start filling in a table. I've got for the different potential differences 3, 4.5 volts, 6 volts, 7.5 volts, 9 volts, and 12 volts. And I'm going to fill in the different currents for A, B, C, D, E, and F, each of the ones that we've got here. I honestly should probably spread these out just a little bit. Let me fix this up some. So, if for whatever reason we're not able to get into the full lab, B, C, D, E, F. This is a place where you can actually see the lab happening, so it'll be kind of a simulated lab. We can also take the data, and I'm going to try and put it together in a video so that we can analyze it more thoroughly. All right, let's go ahead and collect our data. So first off, I'm going to set it to 3 volts. I'm going to turn this on, and let's see what we get. Reading my meter. Let's see, we've got, if that's the 500, then this looks to be about 170 milliamp. I'm sorry. Yeah, 170 milliamp. Let me double check that. I'm going to mark that this is milliamp. It's been a little while since I used one of these galvanometers. They're nice because they can kind of take whatever you throw at them. However, here's what I'm going to do. I'm going to bring in a different meter. This is called a DMM. It's a digital multimeter. It's called a multimeter because it can measure pretty much all the things that we want. It's got a voltmeter in here, it's got an ammeter, and it's got an ohm meter where we could measure resistances. So here's what I'm going to do. I'm going to turn this on, and I'm going to see what we've got. Right now, it's reading nothing because I haven't turned the circuit on. I'm going to power this up. Here we go. There we go. And I've got 0.17 amp, which is 170 milliamp, so good. My measurements are staying clear. We may be using these a lot more in class because these devices can be a little bit pickier. So I might get you set up with the galvanometers, the little ammeters there a bit more. That being said, I'm going to stick with the multimeter because I'm more used to it. DMM is what I'm going to go with. Okay, so we've got 170. Here's what I'm going to do. Bump it up to 4.5 volts. And I get 220 milliamp. I'm going to keep recording these in milliamp for the time being. 6 volts. You'll notice that the bulb is getting brighter. Please take note of that. 260 milliamp. 7.5 volts. 300 milliamp. Great. I'm going to spread these out. I'll fill them in as we go, actually. That way it'll make it a little bit better. Okay, so quick heads up on this. Here's the 7.5 volts. We have a very bright bulb. It's kind of hard to look at. And if I bring it back down to 3 volts, it's a much dimmer bulb, something to take note of. All right. We've collected enough data points. In fact, I keep getting about the same number. Multiple measurements is always good. Nice thing about electric circuits is you're going to get about the same thing each time as long as you don't change anything. So here we go. Let's switch things over to our first resistor, resistor B. All right, now this one's marked R7. Here's 3 volts. Let's see what it does. All right, I've got 220, looks like, oops, 220 milliamp. $220. Great. Let's go up to 4.5. I may actually cut off. So you'll notice that I didn't do 9 or 12 volts on this. In one of the other videos you'll watch, when I get about 9 volts on these light bulbs, they're not designed for that. The bulb burns out, and I don't really want to destroy bulbs. There's another video that actually shows me adding too many power packs and burning out one of the light bulbs. So that's why I've cut this one off here. I may need to do the same thing on this R7 because this is, you'll see that it's actually a higher current. Here we go. Let's see. 4.5 volts. It's 330 milliamp. Great. I'm going to go with 6 volts. $450 milliamp. 7.5 volts. That's looking 560 milliamp, maybe 570. It just ticked up to 570. Let's go ahead and do that. 570 milliamp. It'll fluctuate a little bit. Okay. Oh, that's good to note. We're going to stop that one right there. Don't know if you saw that, but we have a little bit of smoke coming off of this. That's a little too much power to be putting through this resistor. Good. I thought about stopping us there, and that also explains why this thing was starting to switch some of its notations. So, I may even need to mark that one that it is damaged and now no longer good. Okay. All right. Let's move on to the next one. We'll come back to that data, see what we come up with. Now, that's one thing to keep in mind on this, and that's one of the reasons why I like doing this kind of in the video. I don't mind losing a little bit of equipment here, but I want to try and cut down on how much we damage in the lab. I thought about not even including that type of resistor because I figured we'd run into some problems with it, and lo and behold, we did. But that's okay. We'll go through and we'll see the data from it and go from there. If you put too much power through some of these components, you can damage them. You can fry them. You could also start a fire. Electronics can be very, very dangerous if you aren't using them properly. All right, here we go. So we're on to resistor C. This one should be pretty good. I'm going to go 3 volts. Turn this on. And I get a really small amount. Looks like 30 milliamps. So here's what I'm going to do. I'm going to change a setting on my meter and see what I come up with. Now this is a fused setting so that if it gets too much current going through it, it'll actually burn something out in my meter, which I don't want to do. That's why I didn't do it with the others. Here we go. So I'm going to turn this on. But it's a much better measurement. I mentioned 30 milliamp. It's actually 26.4 milliamp. This is a higher precision measurement, but it can get damaged if I send the current too high. 4.5 volts. That's 40.4 milliamp is what it's reading. 6 volts. 53.9 milliamp. 7.5 volts. 67.7 milliamp. Now this one I'm going to keep it not on for very long, but I'm going to go up to the 9 and 12 volt. Here we go. So 9 volt, 82.1 milliamp, and 12 volt, here we go, 109.1 pretty much. It was fluctuating some. Ideally, I'd give it some time to stabilize, but I don't want this thing to overheat. Now, resistors will actually take electrical energy and turn it into thermal energy. Now, it's noticeably warm to the touch, but it's not hurting my hand, so that's fine. One other thing that we'll talk about, and you can ask me in class if you'd like, but as resistors change temperature, they can also change what their resistance value is. So it's not surprising that the numbers would fluctuate some. That being said, we collect multiple measurements or multiple data points so that even if one of these is a little off, we can still see overall what's happening. All right. Now, as we move on these resistors, we're actually going to get slightly different results, and they're going to be a little bit better rated for the values that I'm actually giving them. So D, here we go. So resistor D. All right, let's see what we've got. I'm going to turn this back down to 3 volts. Here we go. 3.1 milliamp. Now, there's an additional setting that I can do to go to an even higher precision than this, but for now, we're going to stick with what we've got. 4.5 volts. We've got 4.3 milliamp. Great. On the next one, 5.8 milliamp. Pardon me, 7.5, 7.2 milliamp. 9 volt, 8.7 milliamp. And then finally, 12 volts, 11.5 milliamp. Okay. We got 2 more to collect. Let's see what we come up with. Not very warm at all. All right, here's what we're going to do. I'm going to connect that. Mental note, don't use the 10... don't mention what they are just yet, but don't use the R7s in this experiment. We usually don't. I usually have you look at the R1s because we've got a whole bunch of those. Let's see, D, E. So here we go. Now on this one, I've got an idea that I think I want to switch this out a little bit. I'm going to change some of the settings on my meter so that I can get a little bit higher precision. Okay, here we go. I'm going to go with 3 volts. I'm getting 0.61 milliamp. In fact, let's actually change that out. Now's as good a time as any to introduce you to one other thing that we're probably going to have to keep track of. In real-life circuits, you're about to see, it's common for us to deal with a value not called milliamp, but also called microamp. This is currently, a better measurement of this is 585 microamp, where micro is kept track of by the Greek letter mu. It looks a lot like, it is the same letter that we used for the coefficients of friction. All right, so that's 3 volts. I'm going to bump this up to 4.5, and I get 864 microamp. Bump it up to 6. And I get 1,150 microamp. I'm wondering if at the high levels we're actually going to have to bump it back over to the previous setting. We might have to. 7.5 volts. I get 1,436 microamp. Great. At 9 volts, let's see if we max out our meter. 1,736 microamp. Okay. Let's go up to 12 volts. Okay, I'm going to go ahead and show you this because we've got it. On my meter, it just says 1 with nothing after it. Whenever you see that, it means that we're on too low of a setting and it can't accurately measure it. So we need to go to the next setting up. Now it goes from a 1 instead to an actual number. So whenever you see that 1 with nothing else with it, it means you've maxed out your sensor and we've got to adjust it to something different. Great. This tells me that we've got 2,350 microamp. Now, what I'm actually reading is 2.35 milliamp, but that's the same thing as 2,350 microamp. Resistors, probably not even that warm. I didn't even notice. It's probably psychosomatic. Okay, we got one more to take a look at, and then we'll have all of our data and we can start working with it. Great. See what conclusions we can draw. All right, so here we go. Our last one, here's F. I'm going to collect this data. Here we go. On this one, because of the settings, I know I want to go back down to microamp. Here we go. So 3 volts. I've got 286 microamp. Great. 4.5 volts. I've got 428 microamp. It's going back and forth between 27 and 28. That's okay. 6 volts. About 570 microamp. Okay. Turn that off. 7.5. About 710 microamp. 9. 857 microamp. Great. 12. Powered on. Our last data point, 1,135 microamp. Great. All right. So there is our data. We're going to take a look at a video in which I get it set up. I'm going to put this into Excel so that we can graph it. What you would be doing in class, and there's a page that'll be made available as well. Also, hopefully we'll be doing this in class. But in case we don't, here's the lab so you can see all the setup on it, all the data that we've collected. You would be graphing it by hand. However, you would probably only be graphing the light bulb, and one other one is normally what we do in class. I figured since I'm doing the video, it'd be easy for me to set up for a lot more that we could draw conclusions of. Now, just so you don't think that there's a bait and switch, I will go ahead and show you the following. But we're going to hopefully find that with our results. So, R7 is marked that it is a 10 ohm resistor. R1 is a 100 ohm. R2 is a 1000 ohm. R3 is a 5,100 ohm resistor, and finally R4 is a 10,000 ohm resistor. There are more, I just haven't got those out because these are the ones that seem most interesting. So we're going to take a look at this data and go from there. Okay, so now we've collected that data for our circuit. We're going to go through and actually analyze some of that data. Now, there are a couple ways that we could do this. What I'm going to do so that we can see them kind of clearly, because we had what was that, maybe 6 different things that we were looking at. Putting all of those on one graph might be a little bit of a mess. So we're going to go into Excel, pretty similar to what we've worked with the Tracker Labs. I'm going to note this column. I'm just going to pick one here. Let's call this potential diff measured in volts. Okay. We took measurements for 3, 4.5, 6, 7.5, 9, and 12 volts. So I'm going to leave a spot for each of those. Okay. Then I'm going to put current in, well, actually we started off in milliamp. So I'm going to mark that's in milliamp. I'm going to spread these out a little bit so that we can see them a little more clearly, and I may actually zoom in some because this is kind of small. There we go. Great. I'm going to go ahead and type in the ones for the light bulb. We had 170 milliamp, we had 220, 260, 260, and 300. We did not take a measurement at 9 and 12 volts because it would have burnt out my bulb. So here's what I'm going to do. I'm going to when we do math on this, I want to make certain that we've got it in SI. The SI unit for the current is not milliamp, it is amp or ampere. So I'm going to mark another column there, and I'm going to convert these by saying that this, our current, is going to be equal to this number divided by 1,000, and this is what it would be in amp for milliamp. Okay, so I'm going to delete those two. And then here we go. Again, normally you'd be doing this by hand, which would take a lot more time, but we're going to go through and we're going to make a graph. XY scatter plot, we're going to select data, go over here, and here's where I'll tell you what graph that I want. I know normally you've been trained with the whole dependent, independent variable thing, but I'm going to outright tell you what graph I want. I want a potential difference versus current graph, which means our X values, our horizontal, are going to be our current. Let's take the ones in amps. Actually, let's go ahead and drag all the way down. I'm going to get us ready for the future ones we work on. And we want our potential differences. Here we go. I'm going to select those. All right. Here we go. So I've got, this is my graph for the light bulb. In fact, I'm going to mark that. This is the light bulb. Great. Okay, we're going to come back and actually work with this one after we take a look at the other data. But first I'm going to do add trend line. Come on, trend line. Display equation on chart, and we'll go ahead and do a linear. This looks like a pretty linear relationship. And I get a slope of 34.7, whatever the units are. Okay, so here's what I'm going to do. I'm going to save us some time. I'm going to move or copy, move to end, and I'm going to create copy. And we're going to call this, I believe it was R7, was the next one that we took a look at. And its current was 330, 220, not 22, get with the program, 570. There we go. Oh, look, this one's pretty linear too. Nice straight line. That's something to take note of. All right, here we go. I'm going to move or copy, move to end, create copy. This is the nice thing about working with Excel. It automatically updates things. I think the next one was R1. So here we go. This one we started filling in more of them. Now we had 26.4, 40.4, 53.9, 67.7, not 57.7, 82.1, and 109.1. Ooh, look at that data. All right, let's keep going. I think the next one was marked R2. Can't remember. That's okay, we'll just call it R2. Great, filling this in, pardon me, 3.1, 4.3, 5.8, 7.2, 8.7, and 11.5. Hey, look at that. Once again, surprisingly linear. I'm starting to think that there's a relationship that we have here. Move or copy, create copy, move to end. I think this one was R3. Okay. On this one, I believe we switched over to microamp. Let's see. Yeah. Hang on. So light bulb, R7, R1, R2, yeah, R3. Okay, great. This one I believe we switched over to microamp. So here's what I'm going to do. I'm going to add 3 more zeros on here because it's a factor of 1,000,000. Great. I'm going to drag this down. Although right now it's linear because it still has the old data in there. 585, 864, 1150, 1436, 1736, and finally 2350. And like that, we end up with, once again, a straight line. Okay, move or copy. We've got one more to take a look at. I think this one may have actually been R5, but I'm just going to call it R4. Doesn't actually matter. It's the last one in our grouping. 286, 428, 570, 710, 857, and 1135. Great. Okay. So, we once again end up with a pretty straight line. Let's start talking about this, because clearly there's a relationship of some kind. There's a direct, or there appears to be a direct relationship between the potential difference and the current. If I double the potential difference, I end up with about double the current. So for instance, we go from 3 and about 290, and then we double it up to 6, and we end up with about 570, 580. So when you look at this, when we double the potential difference, we end up doubling the current. So we go from here up to here. And we end up with from here over to here. We end up about double. We have a linear relationship. In fact, you can see here our best fit line is y equals some number times x minus our y-intercept. And if you'll notice, our y-intercept is actually a really small number. It looks pretty close to 0. Our line is actually going to go pretty much through 0, 0. Same thing with this one. Our y-intercept is pretty small. It's going to go pretty close to 0, 0. Same thing with this one. This one's off by a little bit more. It might hit more like here, maybe, but we're still pretty close to the origin there. Let's see on this one, R1. This one's got a pretty small y-intercept. It's going to be, yeah, so it might actually head over here. I'm not certain I'm reading it quite right. But we can see that it's still pretty close through the 0, 0. You can imagine extending that line. R7, one of the first ones we looked at, far fewer data points. That was the one that started smoking because we probably overloaded it a little bit. But you can see a nice linear relationship, and it's still going to go pretty much through 0, 0. Let's go back to the light bulb. Here's where we see a noticeable change. We have a nice linear relationship, but that thing is not going to go through 0, 0. It's noticeably off. This is where we set up the idea of what is and is not an ohmic resistor. And we're going to introduce Ohm's Law. That's actually what we're seeing with the data, that there is a direct relationship between the potential difference and the current. And what we're going to find is that that relationship is basically whatever the scale or whatever the slope is of that line is what we now call the resistance. So the resistance of this light bulb might be described as something like about 35 ohms, because we put in volts and amps, so when we work with that, we should end up with the SI unit for resistance, which is ohms. This is about 35 ohms, but it's not going to be an ohmic resistor because it does not fully satisfy Ohm's law. More on that here in a little bit. R7. Let's take a look at this one. Now, at the very end, right before we switched over to this, I pointed out to you that those resistors are actually marked with specific numbers. So this one, the very first one next to the light bulb, was a 10 ohm resistor. When we look at the slope, we're a little bit off. We actually measured it at 13 ohm. That being said, it doesn't help that it was starting to smoke there at the end. We were probably putting it outside of its operating range, and we may have damaged it. The next one, R1. We said that that one should be a 100 ohm. We're a little bit off. We've got about 109. Now, one of the things that I'll point out to you is on these resistors, even though they're marked that they're 10 ohm, 100 ohm, and so forth, they actually, because they're, well, mass-produced, they're... Pardon me. They're not exactly the values that they're marked. They're very close, and they're within a certain what's called tolerance. There's actually a band color on them that will tell you about what their tolerance is. Particularly for these, they're usually plus or minus 5%. So they're supposed to be anywhere from 95 to about 108. That being, or not 108, 105. And so this one seems a little outside of that. We might go through and I can double check my measurements. Maybe some of my equipment is off. Or maybe the resistors have been maybe damaged a little bit from some of the things that we've put them through over the years. That being said, we're still pretty close in the ballpark. We're at about 109, so we're about 10% above. All right, the next one was a 1,000 ohm resistor. Well, that one is right at about the 5%, give or take. We're a little above, but we've got 1,058, 59, so about 1,060. So we're a little above. It's possible that my equipment might be a little bit off. That being said, we can see a nice smooth line, and our slope is about 1,000. This is a 1,000 ohm resistor, or at least that's what it's spec'd at. The next one was a 5,100 ohm resistor. Now this one we get a nice line on, and on top of that we can also see that we've got 5,099.8. We pretty much bullseyed that one at a 5,100 ohm resistor. So maybe it could still be that my equipment might be a little bit off. That being said, looks like a pretty good resistance. And then finally on this one, the last one that we took a look at, that one was a 10,000 ohm resistor. We see that we got a value for our slope of 10,584. So that's probably right at about the 5% give or take that it's spec'd at. So I can't tell if my equipment is slightly off in the measurements. It very well might be. We probably could have done a better job on getting some higher precision measurements, or if I've damaged some of the resistors, or a combination of those two. That being said, we can see the relationship that we're about to introduce for Ohm's Law, and we have a pretty good measurement that matches our real-life values. Ohm's Law basically predicts that for the resistors that we're using, as long as they are ohmic resistors, they obey Ohm's Law, which says as we increase the potential difference, the current will increase by the same factor. And whatever our slope of that is, whatever the offset is how we define the resistance of the resistor. So that's what we've got. Okay, so finishing up on what we just saw. We went over and we looked at the data. Again, we had the light bulb. We got that at about maybe 35 ohms or so. The 10 ohm resistor, R7, we got at about 13 ohms, but I'm pretty certain I can actually tell that part of it has melted. I think I subjected it to a little too much. Anyway, our 100 ohm, we were a little bit off. We got about 109, though that's still pretty close to our value. 1,000 ohm, 5,100, we got on there pretty spot on, and then 10,000. So the rest of them were off a little bit. There are a bunch of things that could account for that, and it may also be that they may not be to that precision, though the gold band usually means plus or minus 5%. That being said, not terribly important. We can see the relationship, and that's the most important thing. So let's talk about what we conclude from this. Now, there was a gentleman by the name of Ohm who actually did an experiment almost identical to what we set up just a long time ago. He noticed this relationship, and later, after he put forth that relationship, it became known as Ohm's Law. And what Ohm actually set up was the following. He said that there seemed to be, for a given resistor, you would find that if you doubled the potential difference, then you would end up with double the current. You kept getting the same value. You'd have a linear response, or a linear relationship. And so he took and he said, depending on what that slope is, we're going to call that the resistance, because the harder it is for charges to go through, you'd have a higher potential difference, but you'd have a lower current, fewer charges moving through. This is actually what Ohm put forward, and it was basically, he was defining this concept that we now call resistance as being the ratio of the potential difference you put across a resistor divided by the current that ends up going through it. Now, while this is actually what Ohm originally developed and set up the idea of, it's not usually how we write Ohm's Law. Ohm's Law is best represented, at least the way that I prefer, as delta V, our potential difference, is equal to our current, I, times the resistance of the resistor, R. So this is Ohm's Law. And this is how we're going to see it in my class. Now that being said, on the AP equation sheet, if I am not mistaken, they have the following relationship. That the current is equal to the potential difference, delta V, divided by R. I actually have no idea why they have it written that way. I'm certain there's a reason of some kind, but anyway. So these are the different ways that you could see it. There's also the one that we saw just a moment ago, another way of writing it, that R equals delta V divided by I. All of these are different ways of writing Ohm's Law, and you can find them mathematically, algebraically, by moving things around. My preferred is delta V equals IR, so we will be using that in all the videos and things that we develop from here. So, for example, let's take some of our data and we can actually double check it real quick. So I erased my data here, but I did write it down. Let's say for, I'm going to avoid the light bulb and the 10 ohm resistor. Actually, real quick, let's talk about that. All of the regular resistors followed Ohm's Law pretty well. We had a linear relationship. When I doubled the potential difference, I ended up with twice the current. Not only were they straight lines, but they actually followed all of Ohm's Law. Delta V equals IR. Now, when you look, if you want, rewind, you're going to find that they would have plus some intercept. where this was our current, this was the slope that we found, this was our current, and here was our potential difference. And they'd have plus B, our y-intercept, but for all of the resistors, that number was very close to 0, which means, aside from some experimental error, all of those lines went through 0, 0. Our y-intercept was pretty close to 0. That means that they're ohmic resistors. They follow Ohm's law. Now, the light bulb, at least in the range that we looked at, was still a linear relationship, but it had the following. Delta V equals IR plus whatever that y-intercept was. That's why I made a point of saying that the light bulb did not go through the origin. Therefore, this is not Ohm's law because this is not 0. Ohm's law says this, and it comes from, as we said here, there's no additional terms that go into that. So the light bulb is technically what we call a non-ohmic resistor. In other words, it does not properly follow Ohm's law. Now that we've established that, we are promptly going to forget that for pretty much everything we do in class. We're going to treat resistors exactly like they were light bulbs and that they perfectly follow Ohm's law. So we're going to bend reality a little bit. That being said, I prefer you all working with light bulbs because you can kind of think about what they do, whereas resistors, you just kind of see them doing the same thing unless, of course, they start smoking. That means you've done something wrong. All right, so let's check some of our data real quick. I'm not going to look at the light bulb because we know that the light bulb is a little bit off. Well, actually, let's go ahead and take a look at the light bulb for that matter. We said that it was 3 volts. In fact, let me write this in my colors. Let's apply Ohm's law to it and see what we come up with. We know the slope of that light bulb's line was actually about 35 ohms, which is probably a pretty good representation of what its resistance really is. That being said, we said that delta V was 3 volts, and that's going to be equal to our current, which for our light bulb was 170, 0.170 amp, times our resistance. So for the light bulb, we end up that Ohm's law would predict that its resistance would be 3 divided by 0.170. We end up with about 17.6 ohms, which is very different than the slope of that line. In fact, if we take another one of their data points, let's say the 7.5 volts on the far end, and we said that that resulted in a resistance times our current on that one was 0.300 amp, 300 milliamp. So I take 3 divided by 0.300, and I end up with 10. We're getting a variable answer. We're not getting the same resistance each time. This is because Ohm's law has no y-intercept. And what we saw when we graphed it was, yes, it was a linear relationship, at least in the region we were looking at, but it did not go through the origin. And therefore, this cannot be properly predicted by Ohm's law, making it a non-ohmic resistor. All right, now that we've got that established, let's look at something that is an ohmic resistor. Let's take a look at I don't know, maybe the 100 ohm resistor. So that's what it should be. We said that for a 3 volt supply, that the 100 ohm resistor had the following. So we're going to have our resistance times our current. We said that it was 26.4 milliamps, so that's 0.0264 amp. That's our current. Remember, milliamp is 1,000 times smaller, so I divide it by 1,000. 26.4 divided by 1,000. Great, 0.0264. Now I'm going to take 3 divided by that, and I end up with my resistance is equal to 113.6 ohms, which is pretty close to the value that we got. We know that it's over 100 ohms, and we got, with all of our data points, because this is just one data point, that it was about 109 or so. Great. If we look at another one, that's 12 volts, and we end up with a current of 0.109 amp. We would therefore end up with a resistance of, let's see, 12 divided by 0.109, we end up with 110. We keep getting around the same thing. We've got a small fluctuation between 114 and 110, but we're getting about 110 each time. These are ohmic resistors. This is Ohm's law, and in the next video, you'll see how to use it.